Okay, so let's continue on the chapter of the DC glow discharge. And in a previous chapter, we have already known the architecture of the discharge. So in a typical DC discharge apparatus, one can use a vacuum tube and a quartz vacuum tube and use a vacuum system to control the pressure inside the vacuum tube, and place a cathode and an anode, right, at the two ends of the system. And if you apply a high bias voltage, a DC bias voltage across the system, so from the cathode to the anode, so near the cathode side, the potential is negative. And usually when we use a DC sputtering or PECVD power supply, the voltage of the applied voltage is around a few hundred volts. So the cathode is negatively biased, and anode, usually the anode is grounded, so the potential is 0 volt. But there is an electrical field across the chamber. So from the cathode to the anode, the potential is negative, and then gradually increase to about 0 volt or a little bit higher than 0 volt. And all the potential drop exists near the cathode region. So this is what we learned from the previous chapter. And in the DC glow discharge chapter, Chapman, the author of the textbook, the glow discharge processes, Chapman used an example to realize what's the important parts in the DC glow discharge plasma. So the important thing okay. The important thing is that once the plasma is generated, the gas atmosphere is composed of electrons and ions and other neutral particles. Okay, and electrons and ions are charged particles. So the charged particles could lose to a chamber wall when they travel and strike the chamber wall, or maybe lost to the cathode and anode. So if the charge density inside plasma is too low, then the plasma will extinguish. So the plasma will disappear, so that one can keep a continuous glow discharge or keep a continuous plasma. Okay, so in Chapman's textbook, he used an example. If a DC discharge, right? If you operate a DC discharge system and apply a bias voltage and let the current flowing through anode to the cathode with a current density of 0.3 milliamp per centimeter square. Okay, and in this experiment, the area of cathode and the area of anode are 1 centimeter square. Okay, so based on this example or these conditions, one need to keep a plasma density or plasma charge flow of 1.9 times 10 to 15 per centimeter per second across across an unit area. And if the plasma volume, if the distance, right, between cathode and anode is larger than 1 centimeter, then you can consider that for the area of 1 centimeter square and the distance of 1 centimeter, the volume is 1 cube centimeter. 1 cube centimeter. So one need to keep ion and electrons pair production rate of 1.9 times 10 to 15 per cube centimeter per second. Okay, so this is the condition that Chapman analyzed. Okay, so in last hour, class went through the cathode region and the anode region, cathode region and the anode region. Okay, and this hour I will continue on the negative glow region. Okay. Okay, so there are different regions, right? Cathode surface, and then cathode layer, or what it is called cathode region, and then negative glow, and the right end is anode surface and the anode region. Okay, so in last hour we learned that the discharge process in cathode region and in anode region, and this hour we will discuss the discharge process in the negative glow region. Okay, and also in previous chapter we have already known in a typical DC plasma system there are different glow region, different bright plasma region. Okay, so this region can emit light, or what we call this luminous region. Okay, so the brightest luminous region is negative glow. Okay, and positive column is an uniform luminous region. But positive column is not required for plasma for glow discharge. So in previous chapter, I have already talked about this. So in order to keep a continuous plasma or continuous discharge process, one need a cathode anode and the cathode layer or cathode region, and then negative glow, the edge of negative glow. Okay. Okay. So in the negative glow, the first we'd like to know there are different kinds of electrons. So basically there are high energy primary electrons, and then secondary electrons, and then the thermal electrons or ultimate electrons. Okay, so this is based on the process how electrons come to the system, the glow discharge system. So so from a previous chapter, if we look at this discharge tube, the left side is cathode. And cathode is biased negatively, maybe 300 volt or 600 volts, or even one negative 1,000 volt, minus 1,000 volt. So the potential at the cathode surface is negative, right? Relative to the almost 0 volts of the plasma potential. But actually plasma potential usually is a little bit higher than 0 volt. Okay, And most potential drop exists in the cathode layer region. Cathode layer region. So when the positive ion or cation, when the cation travel, right, cation will attracted by the negative potential. So the cation will travel toward the cathode surface, And when they travel across the cathode layer region, they can be accelerated by the negative potential difference, potential drop. Okay, so first the cation will obtain very high energy when they travel across the cathode layer region and then strike the cathode surface. So when the ions strike the cathode surface, they can knock out electron, right? This is called ion bombardment, right? Electron generated by ion bombardment. And once the electrons are knocked out from cathode surface, right, they will accelerate along opposite direction. So again, the negative potential drop here will accelerate electron. Right, so when the electron come out from the cathode surface, they will travel toward the anode, and when they travel across the cathode layer, they will gain very high energy. So these electrons are called primary electron with very high energy. So the first part of the electrons in the negative glow region is primary electrons, right, coming out from the cathode and accelerated by cathode sheaths. So that when the electrons, right, travel across the cathode sheaths, and when they come to the edge of negative glow, these electrons have very high energy, and these are called primary electron. Okay, but at the beginning, this electron will knock out from cathode surface. When they are knocked out, they are secondary electron. But once they are accelerated, they can obtain very high energy. They become an energetic electron. And when the energetic electrons collide with gas atom, right, it can undergo electron impact ionization. So the electron impact ionization will also generate secondary electrons. But these secondary electrons come from the neutral gas atom. Okay? So in the negative glow region, there are primary electrons and then low energy secondary electron. Right? They are knocked out from gas atom. Okay? And since there's since there's a distance, right, or a length of negative glow, right? It depends on the pressure you use. Okay, if the pressure is very high, then the thickness of negative glow is very thin. But if the pressure is low, the thickness of the negative glow will become very long. Okay, and anyway, when electrons, right, travel across negative glow, they keep striking gas atom. Okay, so after multiple collisional process, after many collisional process, the energy of electron will redistributed. So the energy of this electron will become thermalized electron. And the thermalized electron has a special distribution function. And we have already learned that distribution function before. Right? In a thermal plasma, there are a lot of collision or numerous collisional processes. So eventually, the particles, right, including electrons and ions and other neutral particles, their energy will become almost the same. And this is called thermal equilibrium condition. So there are a lot of thermal electrons in the negative glow after multiple collision process. So actually, there are three types of electrons: a high energy primary electron, and a low energy secondary electron, and thermal electron. And in Chapman's textbook, he gave the numbers of these electrons of 1 torr of DC growth discharge. So for per cube centimeter, the primary electron, the number of primary electrons is about 10 to 6, and secondary electron is about 10 to 7, and ultimate electron is about 10 to 9. So in the negative glow, most the electrons are ultimate electron or thermalized or thermal equilibrium electrons. And this figure shows the electron energy distribution function of thermal electron or ultimate electron. And this function is Maxwellian-Boltzmann, follows the Maxwellian-Boltzmann distribution. So for example, if we said that the average electron temperature is 1 electron volt, for example, 1 electron volt. So here is 1 electron volt, 1 electron volt. But the actual distribution of the electron energy follow this curve. Okay. For the 1 eV, a thermal electron, the distribution curve, electron energy distribution curve, is this one. And if the average electron energy is 2 electron volt, 2 eV, the distribution of the energy distribution of electrons follows the second curve. So you can see the 2 eV is here. So most electrons have energies lower than 2 electron volts, actually. Okay, based on this curve. But there are some high energy electrons, right, in this region. And this part is called high energy tail. Right? So if the average electron energy is 3 eV, the curve looks like the third curve. Okay, and for a plasma, if we want to generate plasma, we need to flow gas inside a plasma system. So in order to generate, for example, in order to generate argon plasma, we need to flow argon gas in the system. So if we ionize argon plasma, so that the neutral argon atoms become argon cation and electron, right? So that we generate electron and ion pair. And for such reactions, we need to apply an energy higher than the ionization energy of argon gas. Higher than the ionization energy of argon gas. Okay, and if you use other gases or like krypton, also an inert gas, the ionization energy is smaller. Okay, so when we look at this curve, look at this energy distribution curve, we'd like to know how much or what's the ratio of high energy tail, because these electrons have energy higher than ionization energy of gas atom. So they can undergo electron impact ionization. Okay. So even though the average energy of the electron, of the thermalized electron is only 2 electron volts or 3 electron volts, there are some electrons with energy higher than 10 electron volts or even higher than 15 electron volts. So those electrons can ionize gas atom and generate more and more electron and ion pair. Okay, so this part becomes the most important part. Okay, the primary or the fast electrons, right? Their density are too low. The primary electrons, the density are very low. Even the secondary electron, the density is also low. But the ultimate electron or thermal electron, their density are very high. So if there are small ratio of the high energy tail, these electrons might have enough density to undergo the ionization process. Okay, so the most important part in the negative glow region is the thermal electrons, and since the distribution curve follows Maxwellian-Boltzmann distribution, so one can calculate this ratio, the ratio of high energy tail. So it's the F, the function of the energy E, electron energy, higher than E0. E0 is the ionization energy of the gas atoms. So also in Chapman's textbook, in Chapman's book, he gave a table to calculate the fraction of the high energy tail, the fraction of high energy tail. Okay, so for example, in argon plasma, one need 11.56 electron volt to excite neutral argon from ground state to excited state. Okay, so the excitation process need 11.56 eV in the argon discharge system. And if one want to ionize argon, one need to supply 15.76 eV. So this is the ionization energy of argon and excitation energy of argon. Okay. And in the second column is the energy of the thermal electron, average energy of thermal electron. So for example, if we consider the excitation process, if the energy of electron is about 4 electron volt, okay? So the excitation energy is 11.56 electron volts. So that excitation energy is about 2.89 times of the thermal electron energy. So at this condition, the ratio of high energy tail is 1.3 times 10 to minus 1. So it means for a plasma with electron energy of 4 electron volts, about 13% of the electrons can excite argon. So the ratio in the high energy tail is about 13%. 13%. And if the electron energy is 8 electron volt, and then the ratio of high energy electron become 42%. 42%. So most electrons have high energy, high enough high energy to excite argon. Okay, and if we consider the ionization process, so again, if the electron energy is 4 electron volt, and then the calculation gave us a result by about 5% of the electrons belongs to the high energy tail. So the 5% of the electron can ionize argon, and generate electron and ion pair. And if the electron energy is 8 electron volt, and then 28% of the electron belongs to the high energy tail. Okay, and the other table on the right side. Okay, so if we consider the ratio of the high energy tail, ratio of high energy tail, and the electron density. Okay, if we consider both conditions, so in a plasma with 50 millitole of gas pressure and electron density of 10 to 10 per cube centimeter. Okay, so in such a plasma condition, if the average electron energy is 2.5 electron volt, the production rate of electron and ion pair, right, is 9 times 10 to 14 per cube centimeter per second. And if the average electron energy is 3 electron volt, the ion and electron pair production rate is 3.10 to 15 per cube centimeter per second. Okay, so this value, okay, right. So that in that example, we can see the ion electron pair production rate reach this value about 3.8 times 10 to 15 per cube centimeter per second. Okay. Okay. So after this analysis, in this chapter, DC glow discharge chapter, okay, the Chapman also emphasized the importance of negative glow. Okay, so negative glow is a necessary path for a DC glow discharge. And in negative glow, even there are fast electrons, right? Very high energy fast electrons. This electron, right? Their concentration is too low, so they cannot contribute 100% of the ionization. Okay, so you find out that ultimate electron or thermalized electrons are the most important part because these electrons have very high density, and there are high energy tails of these thermalized electron. So this high energy tail, the electron with very high energy in the high energy tails, contribute to the most ionization process in the DC glow discharge. Okay, so this is what Chapman want to say. So in the previous chapter, the nature of plasma, and in this chapter DC glow discharge, the conclusions are the same. The negative glow is the most important part of the DC glow discharge. Okay. 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 And there are other particles or other species inside the plasma. Okay. So Chapman also consider this collisional process. So for example, ion impact ionization. Right. When cation collide with gas atom, they can also cause ionization. Okay, but the cross-section, ionization cross-section. So in the first part, the nature of plasma, we have already known the probability of the successful reaction. Right, is in the plasma reactions, one use the cross-section as a unit to represent the possibility of a successful collisional process. Okay, so the ion impact ionization, the cross-section is very small, so this part can be ignored. Okay, and the second part is also important. This is the two-step ionization process. Okay. In the plasma, there are different species. Right? There are electrons, ions, neutral particles, and photons. Okay. So the most gas atoms become neutral particles in the plasma, not ions. Ions and electrons are the small portion of the plasma. Okay. So in the plasma gas, most of the gas atoms are in neutral state. And there are low energy neutral states and high energy neutral state. Okay. So the high energy neutral state is also called a metastable. Okay. So for argon gas, the energy to excite argon from ground level to metastable state require 11.56 electron volt. 11.56 electron volt. Okay, and then one can ionize metastable. If you can increase the energy of the species from 11.56 electron volt to 15.76 electron volt. Okay, so one can ionize metastable species with only about 4.2 electron volt. So this kind of process need two-step ionization process. First step to excite neutrals from ground state to metastable state, and then the second step to ionize metastable state into argon ion. Okay, and it requires only 4.2 eV for ionization of argon metastable. So again, Chapman calculate the conditions for this two-step ionization process. So one can see if the average energy of electron is 4 eV, and then the ionization production rate for the two-step ionization process is about 2.4 times 10 to 13. So compared to the previous process, okay, the thermal electrons and they undergoes the electron impact ionization. The ion and electron pair production rate can reach 10 to 15, right? If the energy of electron is about 3 electron volt or 4 electron volt. And for the two-step ionization process, the production rate of electron and ion pairs is about 10 to 13. So it is about 1% of the ionization process by thermal electron. Okay, contribute about 1%. So the summary of the main source for ionization in the DC glow discharge, okay, list here. Okay, so electron impact ionization by thermal electrons in the negative glow is the most important part. Okay, and then also in the negative glow, the two-step ionization process contribute about 1% of these electron and ion pairs. Okay, and some electron impact ionization and secondary electron emission by the ion bombardment on a cathode surface. Okay, so there are processes. So the most important part is inside the negative glow. Okay, and then some of the ionization process is caused by the electron impact ionization. Ion impact and of the cathode surface and cause the secondary electron emission. Okay. Okay. So also okay, and also in this chapter, this reaction is also important because in the previous calculations, and Chapman and other scientists found out that in the cathode dark space, even though the energy of the electron keep increasing, and this high energy electron might collide with gas atom and generate electron and ion pair, but after the calculation, Chapman found out in the cathode layer region or in the cathode region, these ionization processes are not enough to keep a very high ion and electron production rate. Okay. So the negative glow is the most important part, and most electron and ion pairs are generated in the negative glow. And when this cation is charged positively. Okay. So the cation will be attracted by the negative potential drop and travel toward the cathode surface. Okay, so the cation from negative glow become very important, right? And eventually, this cation, right, undergoes replacement reaction and then reach the surface of cathode. With very high energy, and this high energy cation bombard the surface of cathode and then cause the secondary electron emission from cathode, and keep this process keep going and going. So even though some of the so even though some of the charged particles might lost to a chamber wall or to the surface of cathode and anode, the system can generate enough electron and ion pair in time, so that the concentration of electrons and ions are high enough to keep continuous glow discharge. Okay. So any question? Okay. The next chapter is RF discharge. So in a plasma system, right, depends on your design. Right? You might need RF power supply to generate a continuous plasma. Okay, so the new chapter is RF discharge. And basically there are two types of RF discharge. One is capacitive type discharge. The other one is inductive type discharge. And our class will just focus on a capacitive type discharge. Okay, because in industry, if you want to generate a low temperature plasma, right, non-equilibrium low temperature plasma, you need a capacitive discharge system. If you use inductive type discharge, usually you will generate a thermal plasma. So thermal plasma can be used in different applications. For example, the thermal plasma can be used to melt metals, or to fuse different parts of materials together. So, but for the electronic applications and for the surface coatings and surface treatments, sometimes we don't like to have such high temperature plasma. So in order to generate a low temperature plasma, one need to use capacitive type glow discharge, capacitive type. Okay. So at the beginning of the chapter, in Chapman's book, right, at the beginning, he just pointed out why people use RF power supply rather than just use DC power supply to generate plasma. Why? There must be a reason. Right? There must be reasons. Okay, so depends on your application. Your application. Sometimes you might to process a piece of metal. Metal is a conductor. Right? Sometimes you might like to process a piece of glass. Glass is insulator. Okay. So tomorrow in the next hour, I will go through this part. What's the difference if one use DC power supply, right, and place a piece of insulator on a surface of cathode. If one use a DC power supply, and if one use a high frequency AC power supply, what are the differences? What are the differences? I will let you know in the next hour. Okay. Okay. Class dismissed.